Hi and a very good day. So in this video session, I will continue discussing on one topic under univariate modeling, which is adaptive response rate exponential smoothing, right? So the difference between this technique and another exponential smoothing technique. Okay, so normally we assume that the smoothing parameter that we use is constant all time periods. Okay, we choose first alpha equals to 0.2, beta is equals to 0.8, and so on, right? But the idea by using this technique is suppose that the constant smoothing parameter is not suitable and we need a smoothing parameter which changes across time period. Okay, for example, suppose that there will be a changes in our preference, because of technological changes or innovation, and these changes could be either permanent or it may affect temporarily. Because of this, our observation might be not suitable to have a constant smoothing parameter. Now we have an alternative whereby the ARRES technique was developed to cater the non-constant parameter, which is, as we can see here, the element of AT here. You see that, instead of we use A. So this is actually the formula for our one step ahead forecast is actually the same as single exponential smoothing, but instead of we use the constant alpha, now your alpha have the subscript of T there. It means that it changes across time period. So the formula to get the alpha T is the absolute of ET over AET. What is ET? What is AET? ET is the smooth average error, while AET is the smooth absolute error. So you need to calculate the error first, and then from the error value we can estimate the alpha value, the smoothing constant across the time by using this equation. But notice that we still need a smoothing constant parameter beta, which is to smooth the average error and the absolute error, right? So the idea of using ARRES model is we does not require to find the best alpha, because there is no single best alpha value. It is the alpha, the constant parameter itself vary over time. Alright, so that's why I want to highlight here, we use alpha subscript T there to say that the alpha is changes across time. Again, let's take a look at how we can fit the ARRES model using Excel, right? So let's take a look at our example here. We will use the same data set as our previous example. Now suppose that you have the observation here, the actual value y, and then as we can see here, to estimate, to calculate the alpha T there, you need the average error and the absolute error. So that's why for this purpose of calculation you will need your error, whereby the error is the actual minus fitted, right? So you will have your y hat here. That's how we set up our Excel if we want to use ARRES model. So now we need an ET and also AET, right? So this you have to refer your formulation here, ET and ET, and lastly our alpha T, For this purpose, I just put AT. Okay, alpha T. Okay, right. So before we begin, we need an initial setup, okay, to run it in Excel, right? So suppose that here, okay, in this example, we will use, okay, the initial value for our non-constant parameter should equals to 0.2, and we need beta. Okay, beta here to smooth the average error and the absolute error. So the beta here we will use 0.2. Right, so what are the initial value for this particular row? Okay, y hat is actually equals to the actual value, so we just take the y hat 1 equals to y1. Okay, and for error, since that the actual value is equals to the fitted value, so the error is 0, and we cannot that's why, okay, for ET and AET also 0. Okay, so this is the initial setup. Alright, so now we are ready to put the formula into our Excel. Alright, so refer back. Okay, our y hat is one step ahead. Okay, one step ahead means that, okay, y hat 2 equals to, okay, equals to our alpha T times, okay, our alpha T, okay, times the, okay, the y1, right, the actual value of your y1, plus, okay, 1 minus alpha T, okay, times your y hat. Okay, this is the first setup for our estimated value, right? For error, just simply as actual minus fitted. Alright, for ET, okay, so for ET, this is actually, okay, you can put 0.2 like this, or you can refer to a cell like this, right? I lock here. Okay, times, okay, times the, okay, times, right, times the, okay, ET here is actually, okay, beta ET, so ET here is ET, okay, plus, okay, 1 minus, right, times the pass of pass ET. Okay, our enter, right, and then, okay, next again this value, okay, times, okay, times the absolute ET here, okay, plus, okay, 1 minus beta, okay, times the pass AET, and then you click enter. Right, for AT here is absolute, okay, absolute ET over AET. Okay, so as we can see here, they produce you an error message here. Okay, suppose that we drag, we will also have an error value here. Okay, so how to fix this? Okay, that's why, okay, we still need this initial alpha T, not only at T equals to 1, but also at T equals to 2, and also T equals to 3. Okay, by using this technique, okay, the error value will be solved, and then you can drag, right? Okay, and drag, then you can drag, right? Okay, so this is actually your ARRES model. Okay, you can make it more tidy by specifying the decimal places, right? Okay, so to get the MSE, we simply calculate the error square. Okay, and then okay, right. Okay, MSE is equals to the summation of this over how many observation? 38. Right, so this is your MSE. Okay, so suppose that we want to forecast at 1998, right? So we just, okay, what we do, okay, it is actually equals to, okay, equals to okay, your 80, okay, times, okay, times your past actual value, okay, plus 1 over minus your 80 times your FT here, right? So this is your forecast value. Okay, so basically that's it for our ARRES model. Okay, again, if you have any question, you can reply to this comment. And thank you for listening. That's all. Bye.